Next, we're going to take a look at the vocabulary for graphing a rational function, starting off with what is the definition of a rational function. This is when you have a polynomial divided by a polynomial. So notice that I called the polynomial in the numerator n of x for numerator. We're going to be looking at these later when we're talking about the different pieces of a rational function. And the denominator is d of x for the denominator. An example of a rational function would be 3x squared plus 6x minus 8 in the numerator. That would be our numerator polynomial, all over x minus 1, which would be our denominator polynomial. So notice for the domain, when you were looking at restrictions, that would be when the denominator function is equal to 0, we would have a domain restriction. So you set the denominator of the polynomial not equal to 0 and solve. So for our example function, we would set x minus 1 not equal to 0. So x could not equal 1, adding 1 to both sides. And that would be the domain of our example rational function. Rational functions, because of that division by a variable, can have asymptotes. There's 3 different types of asymptotes. Today we're just going to look at the first 2. The first one is a vertical asymptote. When the denominator equals 0, you can have a vertical asymptote. Again, noticing this d of x is representing the polynomial in the denominator. However, if you can factor the numerator and the denominator cancels with the numerator, you end up with a hole in your graph instead of an asymptote. Looking back at our example rational function, the numerator does not factor. There's nothing that multiplies to negative 24 and adds to 6. So we would have an asymptote at x equals 1. That would be the equation of the asymptote for our example rational function. For horizontal asymptotes, there's 3 different possibilities. The first possibility is when the highest power, or leading degree, in the numerator is smaller than the highest power in the denominator. We had 2 parent functions that had horizontal asymptotes of y equals 0. So to give you an idea of what kind of rational function would give you an asymptote of y equals 0, 1 was the inverse. The degree in the numerator is 0, and the degree in the denominator is 1. 0 is less than 1. The other one was our inverse square. Again, the degree in the numerator is 0, and the degree in the denominator is 2. So that gives you an idea of what kind of functions would have an asymptote of y equals 0. The second one is if the degree of the numerator equals the degree of the denominator. So for example, if we had a function like x squared divided by 3x squared minus 2. The power in the numerator is 2. The power in the denominator is 2. So the asymptote would be the leading coefficient in the numerator. That's this piece right here, a sub n, the leading coefficient in the numerator divided by the leading coefficient of the denominator. So for our example, the leading coefficient of our numerator is 1. The leading coefficient of our denominator is 3. I'm getting the 1 from 1 times x squared, and of course the 3 from the 3 times x squared. So our horizontal asymptote would be y equals 1/3 for that example off to the left there. And finally, if the leading degree of the numerator is greater than the leading degree of the denominator, so this example that we first looked at, we would not have a horizontal asymptote. Slant asymptotes we're going to get into more detail, like I said, in the next day. But real quickly, know that if the leading degree is 1 more in the numerator than the denominator, like our example, we would divide and you ignore the remainder. So the slant asymptote would be equal to the quotient of your rational function. We'll see how that works tomorrow, so don't worry too much if you didn't follow what I just said. The last piece of information that can be helpful to getting a rational function graphed is determining whether or not it has symmetry. So this is a review of something we saw from Unit 1. If you substitute negative x into the function and it equals the original function, meaning all of those negatives end up canceling out because of even powers, then you have y-axis symmetry. If instead you substitute negative x into the function and you can factor a negative out of the function, then you would have origin symmetry. So those can be some helpful pieces of information when you're trying to graph your function.